Ashvin, would you like to share your screen? So our second speaker is Professor Ashvin Vishwanath from Harvard. He will tell us about creating and probing non-Abelian topological order on a quantum processor. Ashvin, please feel free to start when you're ready.
All right, just a second. Let me do that again.
Mm-hmm.
All right, you see my cursor,
Yes.
Zushi?
No, not yes,
No?
yes, I can see it now.
All right, great. Okay, so thanks to Zushi and all the organizers for restarting this series. So hopefully we'll have talks by lots of people reporting on new work that would take a while for us to actually meet in person and hear about. So I'll talk about some work that we've been doing for actually more than a year now. But the new progress is that we've been able to have collaborations with experimental groups and actually implement some of these ideas that we've been talking about. And also in the process, we actually learned quite a few new things. So I'll tell you a little bit about our efforts to try and realize non-Abelian topological order on these controllable quantum processors. Okay, so the first thing that first and most important thing is to thank my collaborators. So this is work done with Nat, Ruben, and earlier with Ryan. And recently we were joined by this group in Quantinuum who worked on the experiment. So it's a large team, but we mainly worked with Mohsen and Hendrik. And that was a really fun collaboration, and I'll tell you a little bit about that towards the end. Okay, so in terms of overview, I'll give you a very brief introduction. I don't think this audience needs much of an introduction. What non-Abelian topological order is. Actually, I toyed with the idea of using this abbreviation just to reference Nat, who was really the sort of the driving force for the part of the project I'll talk about. I'll give you some motivation for why we're interested in non-Abelian topological order. Again, very brief, and the main thing will be about how to realize it, given the constraints we have with these current quantum platforms. And finally, I'll tell you a little bit about the experiment. Okay, so it's easier maybe to start with the why. So there's a lot of interest in non-Abelian topological order, and partly as a route to universal fault-tolerant quantum computing. So this is a distant goal, and this is one of the motivations, but at least for us, this was certainly not the only one. So another thing that has been very exciting for us has been to learn more about non-Abelian topological order in this project. So these states have very subtle kinds of quantum entanglement. And actually the point of view that I've come around to of late is that they're roughly about as different from Abelian topological order as Abelian topological order is from regular short-ranged entangled states. And finally, they're really hard to realize and probe. So there's been a candidate non-Abelian topological phase for decades now, the quantum Hall phase at quantum Hall plateau at 5 halves filling in the quantum Hall effect. But it's really been hard to make a definitive case for that, although many of us believe that it is indeed a non-Abelian topological phase. So trying to circumvent some of these difficulties in the new experimental platforms is kind of a challenge we'd like to address. Okay, so what is non-Abelian topological order? I mean, one way to think about it, of course, is if you have such a phase of matter, it has a very subtle kind of ground state quantum entanglement, a non-local quantum entanglement, which can be precisely characterized. Another way in which people often like to characterize it is in terms of its excitations, which have non-Abelian statistics. So in contrast to Abelian anyons, which you take one around the other or around itself, you get a non-trivial phase. For non-Abelian topological phases, you get excitations, anyon particle-like excitations. You take one around another or around itself, it can change its character, which is sort of shown in this cartoon. Okay, and so there's been a lot of theory on such states. There's a caveat, which I won't spend too much time over here, is that even in trivial phases or even in phases with the Abelian topological order, you can get some kind of excitations or create some kind of defects that share some properties of these non-Abelian particles. For example, the boundaries of 1D topological superconductors or these Majorana defects in the toric code. But here I really want to think about a situation where the ground state has non-Abelian topological order. The excitations are really point-like particles, unlike these defects, and those are the ones that carry the non-Abelian-ness in the system. Okay, so now turning to the question of how do you try to prepare and probe these states. So let me just very briefly recap what the situation is with the Abelian anyons. So of course, we have there's extremely good evidence for them to be realized in the quantum Hall effect, the fractional quantum Hall effect. And more recently, there have been some small system sizes realizations in these synthetic quantum platforms using Rydberg atoms and also on these superconducting qubit arrays on Google's Sigmor chip. So these are prepared in what we roughly call a unitary preparation method. So either some kind of adiabatic sweep or by applying gates and starting with a trivial state and applying many layers of gates until you finally end up in the fixed point of the toric code phase. Okay, and of course, this preparation has worked for small system sizes, but it is limited. And one of the limitations is that the depth of the unitary circuit that you need to make this scales with system size. So you've got to apply gates in a certain predefined order. And if you look at the total depth of this circuit, it ends up being, if the system size is L, the linear size, the depth of the circuit is also scales with that system size. So we were really interested in trying to speed up this process, both from this theoretical point of view that, can you actually create this kind of state in a shorter depth? It cannot be unitary anymore because that would actually, like Marvin was saying, that would actually collapse you into the same state of matter. You'd have to introduce something non-unitary in the preparation. And from a practical point of view, maybe this could allow us to realize more exotic states of matter, in particular non-Abelian phases. So that's how we really got into this, trying to find a quicker, fast preparation scheme for these exotic states. And the key ingredient that we'll use is really wave function collapse measurement, and then utilizing the result of that measurement to feed forward and determine the next layer of unitaries based on the result of that measurement. Yeah, and so it's actually known for a long time. You can do this and use this to create Abelian topological phases like the toric code. Surprisingly, the first realization was very recently, actually a collaboration with the same experimental group over the past few months. We realized the toric code using the same scheme. But the question is, can you actually realize more exotic states, which is what I'll talk about today, trying to realize a non-Abelian topological order on a system of qubits. The particular one that we'll talk about is based on this non-Abelian group. So just like the Z2 group was the basis for the toric code topological order, the group that we'll be interested in here is the non-Abelian group, the symmetries of a square. D4, it has rotations and reflections, which do not commute with each other. And you can think of that as a gauge theory, a discrete gauge theory, which is non-Abelian. And we'll create the quantum state that corresponds to that topological order. Again, we'll show that it has certain properties which only occur because of its non-Abelian nature, and we'll invoke this measurement as a tool in its preparation. Okay, so before I turn to that, let me just remind you about how one can use measurement to quickly prepare Abelian states, in particular the toric code ground state. Okay, so this is the cartoon of the wave function of the toric code on the square lattice. On the center of every bond, you have a spin either up or down. And when it's down, we'll represent it by a line. So the toric code Hamiltonian, the ground state, is a quantum superposition of closed loops where the segments of the loop are defined by the spins being down on the bonds. Okay, so how would you prepare this state? So one way to do it is to start with a state that naturally satisfies this term, the stabilizer, the product of sigma x around a paquette, and then look at the first term, which also needs to be satisfied in order to find the ground state. So violations of these terms actually correspond to E anyons, so excitations above the ground state, and you need to clean them up. And if you can clean them up and eliminate all these E anyons, you would have realized this closed loop configuration. Whenever you have an excitation of the E anion, it implies that one of these lines has ended, and that is the defect that is taking you out of the ground state. Okay, so one approach, which has been around for many years now, is start with the state, eigenstate of sigma x on all the bonds. You automatically satisfy this term, and then go and measure this particular stabilizer. Go and measure this product of sigma c on every vertex. So you have not measured everything, so you still have some non-trivial quantum entanglement present in the wave function. And it's very important that you keep track of the result of the measurements. And you find that this stabilizer sometimes is satisfied, that's fine. But sometimes your measurement yields excited stabilizer, and those correspond to the locations of these E particles. Okay, and in the final step, which is very important, you clean up the state. You use the information that you got from the previous measurement step, and you clean it up, and you get the pristine Z2 topological order, the ground state of this precise Hamiltonian. Okay, so let's take a look at this cleanup step in a little more detail, which turns out to be important. So this cleanup step is you, for example, found a violation of the stabilizer product of Z over here. You found another violation somewhere else over here, and you can correct it simply by implementing this product of X, applying these gates on the intervening links. Okay, so once you do that, you've sort of taken these E anyons and you've annihilated them. You're guaranteed to get an even number of E anyons in this process, so you're always guaranteed to be able to clean them up. You could try to be efficient and use the minimum number of these X operators, but for our purposes, as long as there is a way to clean them up, we're happy with that, and we can always do it. Okay, so so this is a string operator. It contains many, it contains operators that are proportional to the length, the separation between these E anyons. But as you can see, they all commute. Okay, so they all commute. It means you can apply them all together. So in a single step, you can clean up these excitations, and you can end up in the toric code ground state. Okay, so this gives you a way to prepare the toric code in finite depth. So you do a set of measurements, and then you apply the string operator, and you're done. Okay, so this is one approach, and you can ask, can I generalize it? Because all these individual steps seem to be generalizable for non-Abelian anyons. So imagine there's some similar situation. You start with some product state, you go and measure stabilizers that tell you where the non-Abelian anyons are, and then can you just clean it up and get the ground state of a non-Abelian topological phase. Okay, now it turns out the place where this naive approach fails is in the cleanup step. Okay, so there, in order to pair up these non-Abelian anyons, you need to apply a string operator, unitary operator that will pair them up and annihilate them. But this string operator turns out to be extremely complicated. There is no way to apply it all at one go. You have to apply it sequentially, This ends up giving you a circuit depth that's proportional to the separation between the non-abelian anyons. Okay, so in a way, you've returned to the starting point. You may as well as, at least from this point of view of this linear depth preparation, you may as well have started using the unitary preparation, which has a similar scaling with system size. Okay, so this naive approach fails because the string operators that create or annihilate pairs of non-abelians are complex. And actually, this is something we learned during the course of this project, and it was pointed out, I think, recently by Bo and Shi. This is a way in which non-abelian anyons really differ from abelian anyons. They're both created by string operators. They're not local extensions, but the complexity of the string is very different from the abelian and non-abelian cases. Okay, so the naive approach does not work. We need a different approach to get to these non-abelian anyons, non-abelian topological order. Okay, so one clue comes from this another piece of technology that was previously known, which was at that time seen as a technical improvement. So when people thought of this way of preparing toric code by measurement, you measure this product of sigma z around the four sides. So of course, measuring a product of four operators is cumbersome. You'd like to make this a single side measurement. So in order to do that, people had introduced ancilla qubits on the vertices of the same lattice. They apply a gate, which essentially transports the information about the stabilizer to the ancilla qubits. The particular gate turns out to be a control Z, a product of control Z's acting on the bond and vertex qubits. Once you do that, you're free to just measure the central qubit, and that will report on the value of the stabilizer that you wanted to measure. Okay, so in this implementation, you act with this, again, just one layer of unitary operators, one or two layers of unitary operators, and then simply measure the central qubit, and that will end up giving you this the location of the E particles, which you can then pair up in the final step. Okay, so it turns out this actually is hints at a more general mechanism at play, which is what we found, which is what we reported in this particular paper, which is that you can think of this process as a gauging map. Okay, so your input is some state which is short-range entangled. It's a Z2 symmetric state, a paramagnet, if you like. You entangle it with you combine it with some ancillas that are in some predefined state. Then you go through this gauging map. I just briefly hinted at it. It's a collection of these control Z's, but for our purposes, it's simply something that is finite depth, a couple of layers, let's say. It's independent of the size of the system. And then at the end of the day, you go and measure these blue qubits, and you can do the cleanup, and you end up with the toric code ground state. Okay, so this is sort of a more general engine, if you like. If you started with the simple paramagnet, all the spins pointing along the x direction, you get the fixed point wave function of the toric code, but actually it could be anywhere in the Z2 symmetric phase. Ultimately, it'll give you a wave function that is a Z2 deconfined wave function. Okay, so this is a more general kind of map. You give me an abelian symmetry, you can go through this process and gauge that symmetry and be in the topologically ordered phase with that particular group being the gauge group. Okay, so this is kind of a gadget that we can use, and we can use it to build more complex kinds of quantum states. Okay, maybe I'll pause here for a second if there are any questions before I kind of talk about the non-abelian part. No?
I have a quick question.
So, yeah.
Yeah, so in the diagram on the slide, you say measure the blue guy, the product, while previously you said you're measuring the ancilla. Which one?
Yeah,
so
that's a good. Yeah, so here in this color, this notation, the blue is actually at the vertex.
Okay.
And the red is on the bond. So you're right. It's at the end of the day, what is the ancilla and what is the physical qubit have swatched. Yeah. That's kind of the duality, if you like. So the Ising model, the Z2 symmetric wave function is sitting on the vertices, ancillars on the bonds, ancillar in the sense that we have initialized it in a predefined state. You go through this map and then you go and measure the things on the vertices. I've shown the outcome where all of them are plus. But in general, some of them are plus, some of them are minus. And based on the measurement outcome, you've got to do the gates. So of course, project out is one option, but it's not a very good option because it's extremely unlikely you'll get all the plus as the measurement outcome. So that's not a scalable way of preparing the state. So in general, you get plus and minus. Very important you record what you get. And based on that, you decide which string operator to apply and just apply it in one step.
I see.
And you end up getting the pristine toric code wave function.
And the gauging map of these control Z's, this cluster.
Yeah, that's all it is. Yeah, it's just control Z's. It creates a cluster state.
Okay, thank you.
Great. Okay, so now let me talk about how we can use this sequentially, or use this with other input states to realize non-Abelian topological order. Okay, so again, I won't go into too many details, but this is essentially how we proposed to prepare this D4 quantum double. You can think of it in two different ways. They end up giving you the same result at the end of the day. And again, that is a little bit surprising to us, but you can show explicitly that you get the same outcome. So the first is that you can use this Kramers-Vanier or gauging map to create Abelian topological order with Z2 times Z2 topological order. It's called the color code. So that is possible. And then you can do another layer. So you're doing it sequentially, where you swap, where you kind of swap these. There's a symmetry of swapping these two Z2s, and you take that symmetry and go through the gauging map, and it ends up giving you this group, which turns out to be the same as D4, the symmetries of the square. Okay, that's one way of doing it. Another way of doing it, which is also nice to think about, is instead of the initial state as being a trivial paramagnet, you can think of a state that has three Z2 symmetries. So I've denoted them by three different colors. We'll use this color convention as we go along. And you can create them in a symmetry protected topological phase to begin with protected by the symmetry, a particular kind called this type 3 SPT. And then you can go through this gauging map for the three Z2s. And it turns out the output of that is also a non-Abelian topological order. In fact, the same one, this D4 quantum double. Okay, and it turns out this non-Abelian topological order is quite complex. It has 22 anyons. 8 of them are Abelian. Those are like the E particles. Those are like the charges of these Z2, these three Z2s. They remain Abelian excitations. It's really the M particles, the fluxes, if you like, of these symmetries that become non-Abelian. Okay, and in fact, this SPT, one way to think about this SPT is there's this decorated domain wall construction of SPTs. So if I imagine for a moment breaking one of the Z2s, I look at the ordered phase and I look at a domain wall between, say, Z2 being up and down. The domain wall is a one-dimensional system, and the remaining two Z2s are unbroken. So I can think of an SPT with respect to the remaining two Z2s, and they can give me a Haldane chain. So they can give me a 1D SPT that decorates this domain wall. That's really the SPT that one is thinking about as the input state. If you were to gauge that SPT, it's actually easy to convince yourself it will give you a non-Abelian topological phase simply because this 1D SPT, the Haldane chain, has got a twofold degenerate edge state. Okay, so that twofold degeneracy protected by symmetry after you gauge it becomes the internal quantum dimension of a non-Abelian particle. Okay, so it's actually nice to think of a microscopic model, very much like the toric code, where all of this can happen. And there's this beautiful model that builds on earlier work by Yoshida. You can write down this model on the Kagame lattice. You color the Kagame lattice with three colors. That's the red, blue, green that I was talking about. And you write down this Hamiltonian. It's a sum of two kinds of stabilizers. There's a very simple stabilizer, which is a product of three Z's. This is a bit like the one of the stabilizers in the toric code. And then there's another stabilizer that's more complex. It's on the star. It involves X operators, but it also involves control Zs. Okay, and so these are the two kinds of stabilizers. We'd like to get them both to be unity. That's going to be the ground state of this model. So these stabilizers do not commute. That's the difference from the Abelian topological order. So you can convince yourself you can never get a stabilizer, commuting stabilizer Hamiltonian for non-Abelian topological order. If I set the B equal to 1, all of these star terms will commute with one another. Okay, so there is some sense, at least in this B equal to 1 sector, where these are commuting, these A's are commuting. Okay, so we want to prepare the ground state of this, if you like, and we're going to use the same strategy as we did before. Pick some initial state, and then by using measurement, we're going to try and satisfy this A term. Okay, so let me actually, to guide you through that, let me switch to the experiment where I can show you the results of doing all of this as well. So just a brief aside on the experimental system. So this is the hardware that we're going to be talking about. So it's ions. So if you're really interested, it's ytterbium 171 plus. That's the quantum bit. The two levels, the hyperfine levels of that are going to be the quantum bit. So they're trapped along a racetrack. There are 32 of them. And they have a really excellent gate fidelity. This is the single qubit fidelity, and this is the 2 qubit. So it's, I think, the most the highest fidelity available out there for 2 qubits. But really, the thing that is very important to us, one is that there is all-to-all connectivity. You can take any pair of qubits and make them interact. That's the way in which it works. The ions are on this racetrack. You bring them into certain regions where you apply the qubit gates, and then you send them back and hold them in the racetrack. So you have this all-to-all connectivity. And the other thing that is very important for us is that you have the option of doing mid-circuit measurement. And based on the outcome of the measurement, you can change the unitary operators that you apply. So you can apply this the appropriate string operators to clean up and get the ground states. Okay, so this is the only platform right now that has this capability, at least with as many qubits as this, and we were just able to fit our non-Abelian topological phase on this particular system. Okay, so you can ask, what is the point of trying to realize these kind of states on a quantum processor based on gates, especially where you know it's going to work. It's you're kind of guaranteed certain fidelity for the gates. But I think, at least for us, the big challenge was that the systems are actually very limited. So you have a certain number of qubits, you have certain gate fidelity, certain depth that they can apply. With the currently available capabilities, can you actually realize these highly entangled states? Are we kind of there yet? So that was certainly one of the big challenges. The other, it turned out, once you focus on a particular non-Abelian topological order and really study it in depth, we learned things about non-Abelian phases that we actually didn't know before. I'll try to tell you a little bit about that. And it's really a launch pad for more detailed investigations and maybe later on error correction and so on. Okay, so so this is how the ground state preparation goes. I won't walk you through the details, but essentially we pick an initial product state which satisfies these B operators. So those are taken care of. And we're going to use these, these ancillar qubits, these control Z kind of gates, measurements, and then this kind of cleanup in order to create this particular ground state. So here's an example of a result, a ground state that was created on these set of 27 qubits, which have the entanglement connectivity of a torus. You can roughly think of it as being on a torus. Although it's really on this racetrack, the entanglement is really of qubits on a torus. Okay, and these numbers report the measurement of these stabilizers. So this triangle over here is the B stabilizer pointing in that particular direction, and the star is the A stabilizer. And as you can see, all of these numbers are very close to unity, showing that you have prepared the ground state. And the fidelity per side is extremely high. It's over 98%.
Excuse me.
So Zushi,
A stabilizer act on 12 spins?
The A stabilizers act on 12 spins. That's right.
I see. It's doable.
So it's doable again by this. You introduce an ancilla.
Oh, I see.
And you do a set of control Z gates, and the entire information about the A stabilizer is now contained in a single ancilla at the center of this thing. You go measure it, and for example, if it's -1, you can clean it up.
Okay.
Yeah. So yeah, it's kind of amazing. They still got these kind of fidelities at the end of this. I see Zushi has switched on the camera. Am I into the last 5 minutes?
It's better to wrap up soon.
Yeah. Okay, so the next thing we'd like to have created a ground state. The next thing we'd like to do is create a pair of anyons, non-Abelian anyons, and drag them apart and fuse them back into the vacuum. And these are really something that you can do by applying unitary operators. You apply gates, and again, this is the sequence we'd like to follow. Take a string and take it around and collapse it back. So when you apply with the unitary operator, it's just X for this small segment. You notice that there are a pair of opposite plaquettes where the stabilizers are violated. That's this minus value you see over here. The abelian part, the abelian excitation, the star, is actually 0. It's indeterminate because now there's a non-abelian flux there. And then you can drag it around by acting with these string operators. These get more complex as the length increases. So here there are 3 X's. It's also a control Z in between. It gets even more complicated as it goes around, more control Z's. So this is the point that these string operators for non-abelians actually grow with the length of the system, with the length of their separation. At the end of the day, you can fuse them back, and you see that all the stabilizers are back close to the ground state value. They're not as good as before, but it's kind of impressive that they get back close. Okay, you can do something a bit more interesting. You can take a pair of these non-abelians and link them. And when you do that, you don't go back to the vacuum. You get some excitation. The M particles of different colors can be linked, and they'll end up giving you abelian anyons. So that's the red over here. Go through this sequence, you find out at the end of the day, you actually have a pair of plaquettes that are excited. The stars are excited, which refer to the abelian anyons. So you can do this creating, braiding, and annihilating non-abelians on this little torus. Okay, so here's something that we didn't know that we figured out during the course of this project. So let's say you actually take a string operator around the torus. This should give you new ground states. In fact, they do. But sometimes when you take string operators around the torus, like the green and the red, which intersect, you find something interesting. In the ground state, you actually have a single plaquette that's excited. Okay, so in fact, you have a single abelian anyon on the torus. We were used to thinking that anyons always come in pairs. String operator always a pair of anyons. That's true on the sphere, but actually on the torus, you can get a single anyon. And you can actually see it when you braid these non-abelian excitations around the torus. So this is something specific to non-abelian topological order, that you can end up with a single excitation on the torus, and that's marked by the fact that the stabilizer is not in its ground state value. It's actually in the opposite -1 value. Okay, in fact, this is how you end up getting the 22 torus ground states. So we said that this D4 topological order is 22 anyons. The number of ground states on the torus is in 1-to-1 correspondence with the anyons. If you simply had the 3 Z2s and gauge them, you'd get the toric co-degeneracy of 4 cubed, 64 ground states. The reason you have fewer ground states over here is that some of these new ground states that you would have created using the toric code kind of reasoning, they wind up giving you the single excited anyon on the torus. So they're not to be counted as ground states, and you remove them and you get exactly these 22 torus ground states. Yeah, so in fact, in the experiment, they prepared all 22 of these ground states, and they all have excellent fidelities. Okay, so finally, let me make one more point, which is there is an intrinsically non-abelian braiding that you can do and check, whether that actually works with this particular system. So, abelian anyons, they are sensitive to having loops that are linked. E and M particles are linked, you get a -1. And they're actually only sensitive to this kind of pairwise linking. Okay, so they would have a -1 here. For these Olympic rings, you can also say that they're all linked pairwise. You would get some minus sign for abelian anyons. But if you had a set of 3 rings in this configuration, the Borromean rings, you can actually see, if you look at it carefully, no 2 of these rings are actually linked with one another. So let's say you cut out the blue, you can slide the green and red rings apart without any problem. They're not actually linked pairwise with one another. Okay, it's only the 3 of them together that holds the structure together. Okay, so it turns out for our Abelian, if you had an Abelian topological order, this Borromean kind of ring would always be trivial. Okay, it would not be able to see it. But for non-Abelians, in particular our D4 quantum double, if you have M particles with 3 different colors in this non-Abelian order with this kind of space-time diagram, it should end up giving you -1. It should give you a non-trivial phase. Okay, and that's something they can check experimentally. I won't go through the details. Again, it's using these string operators. And experimentally, they get a phase which is very close to e to the I pi. It differs in the second digit. Okay, so let me conclude over here. So I've tried to very quickly tell you a little bit about this creating non-Abelian topological order, and the main point is that this set of 27 ions on this chip actually has the same entanglement as D4 non-Abelian topological order. Okay, that's kind of the clear connection between the two, and it emphasizes some of the unique properties of these non-Abelian states that I talked about. And the key ingredient here was measurement. Can you, the obvious questions are, can you create more complex kinds of non-Abelian anyons like the Fibonacci anyons? And really, ultimately, I think from at least the application point of view, whether you can incorporate things like error correction and create topological qubits. Of course, all of that is for the future. But I think this really opens up, exploring the intersection of quantum information with these more exotic concepts, SPTs, lattice models, topological field theories that have, I think they find a very natural home in this particular setup for realizing these topological quantum bits. Okay, let me stop over here.
Great, thanks, Ashvin, for the very cool talk. So let's do one quick question and then move on to the free discussion part.
I have one quick question. So you mentioned Fibonacci towards the end, but Fibonacci cannot be obtained from the similar trick you play, right? You cannot start with some Abelian SPT and gauge, etc. So how difficult would it be to realize the Fibonacci, given that it's fundamentally qualitatively different from the D4 topological order?
Yeah, so at least as far as we know, we don't have a fast preparation way of doing Fibonacci, of getting the Fibonacci anyons using measurements. It would be nice to prove a no-go theorem. So is it just we weren't smart enough, or is there a no-go theorem for constant depth, but with measurement and and feed forward? It is impossible to create Fibonacci anyons. What we do know is that if you have a topological order which has a Lagrangian subgroup, so a bunch of Abelian anyons that if you condense them, you completely kill the topological order. If you have something like that, we can make it quickly with measurements. That's what we know.
I see.
But we have not been able to prove the no-go theorem. It's very likely it exists, but I can tell you later that there are some key steps that we're not able to prove, which we think is technical. It's not we don't think something is hiding there that can actually violate that. But yeah, you never know with these things, right? Yeah, but even unitary preparation, or if you allow for it's there are different levels at which you can kind of discuss this question. But ultimately, on the existing hardware, can you create Fibonacci anyons? That is sort of the bottom line. And yeah, I think that's an interesting open question.
Okay, thank you.
Great. So before we start the free discussion and before people leave, let me just say that the next set of talks will happen in July, and the details will be sent out via emails. And see you next time. So let me stop the recording now. And